question to take a look at, and let's try to solve that question and go from there. So we'll try to do some problem solving with dependent circuits and then dependent sources, and then we'll see if we can cover one more topic. So this is a 5 amp source. You had a 30 ohm resistor here, followed by another 10 ohms. And this was Vs. And you had a current source here. This was the current I0. And I0 is equal to, if I remember, is equal to 2 amps. Okay. If I0 is 2 amps, calculate the Vs, okay, find Vs and power absorbed by the sources. Okay, so we need to find Vs and the power of the sources. All right, so for us, the critical node here is this node. Okay, let's call this as node N. Okay. Since I0 is equal to 2 amps, we know this will be 2. Okay. 5 amps flows in like this, so this will be 5 amps flowing into the node. Okay. This 2 amps is leaving the node, right? We also know this current, 2 times I0, 2 times 2, that will be equal to 4 amps. Okay, and this is exiting this node like so. That is the direction of current. Okay, the only current that we do not know is this current. Let's call this current as Ix. Okay, we'll call that current as Ix. Okay. Now, if you do KCL at node N, okay, we'll write all the leaving currents positive, and we'll write the entering current as negative. So 5 amps is entering the node, so negative 5. 4 amps is leaving the node, so plus 4. Okay, leaving the node, Ix. This is also exiting the node, so plus 2. Okay, so Ix will be equal to negative 1. Okay. Ix is negative 1, which essentially means that the current is actually flowing in the opposite direction to what is shown here. Okay, that's fine. So once we know Ix, okay, what we can do is we can find Vs. Okay, to find Vs, we'll go here and we'll do a KVL in this loop. Okay. So what I'm going to assume is, since the current flows from this end to this end, this will be the voltage across it. We'll call this as V10. Okay, voltage across the 10 ohms. Here, current flows downwards, so we'll call this as V30, which is the current across the 30 ohms. Okay, so if I write a KVL equation here, okay, this was our KCL. Let's do KVL. Okay, we'll call this as our mesh 1. Okay. So we'll start from here. Okay. So plus 10V, you have V10, okay, plus Vs, okay, minus V30 should be equal to 0, right? All right, so Vs should be equal to V30 minus V10. Okay, V30 minus V10. So when we do V30 minus V10, we'll write this in terms of Ohm's law. Okay, so this will be V10 will be 10 times Ix. Okay, so this will be equal to negative 10 times Ix. All right, and then here you have 30 times I naught. Okay. Now if you substitute the values of I naught and Ix, we should get our answer. So what is I naught? I naught will be equal to 2 negative 10 times minus 1. Okay, so that will be 60 and 10, 70 volts. Okay, so that is Vs, right? So we have two sources. We'll work on both. Actually, we have three sources. Okay, let's try to do one after the other. Okay, what I'll do is I'll do these two. I'll leave this one to you, and I'll show you how to do it. Okay, it's exactly as we do it for the source. The same technique applies here. Okay, so both of them, as you can see, are current sources. Okay, they are similar. So you can try this one, and I'll do this one. Okay. All right, so first let's start with this, then we'll do this one, and I'll give you time so we can confirm the answer that you come up with for the last one, okay? So let's start with Vs, okay? Now, if you want to find the power of the voltage source, right, power of Vs, okay, that will be equal to, right, plus or minus, okay, voltage of the source times current of the source, right? Okay, so in this case, we know the value of Vs, right? Vs is available to us, we just found out Vs. What we don't know is the current, okay? So what we'll do is, let's go here, and at this node, let's call this node as node, let's call this as node A, okay? And over here, what I'll do is, let's mark a current entering the positive, and we'll write it as Is. You can assume it leaving also. If it happens to be in the opposite direction, then you'll get a negative answer. If it happens to be true, that current actually flows in the direction that we have chosen, then the current will be positive. So it doesn't matter whether you pick it coming into the source or leaving the source, eventually we'll get a negative answer if our direction is opposite. Okay? So to find Is, because we know these two currents, we can easily do a KCL here. And we'll say KCL at node A. Okay, so if I do KCL at node A, what am I going to get? So at this point, okay, these two currents are entering the node A. So we'll say negative 2 times I naught, okay, which is the current that flows like this, will eventually come here, right? And then you have negative Ix. Okay. Leaving current is plus Is is equals to 0.
Question.
Yep.
So if the Ix is moving in the opposite direction because it's negative, it should
Yes.
be leaving that node, right?
Yeah.
We know that.
Okay. So it will be the same. I'll explain to you. Okay. So if I assume, okay, give me 1 second. Let me do this, and then I'll do. So as you mentioned, we'll do it over here. Okay, we'll do both of them. Okay. So negative 2 times I naught, right? So this will be minus 2 times 2 minus Ix, write it as negative 1. Okay, plus Is is equals to 0. Okay, so from here you'll get negative 4 and minus 1, so negative 5. Okay, so what you'll do is substitute these values here. Since we got a positive value here, that means current is actually entering the positive. Okay, so current entering the positive means positive power. So PVS will be equal to plus all right. So coming to your question. Okay. So this current, as you mentioned, because we got a negative answer, the true direction of the current is like that, right? So if I'm going to write a KCL equation with the true direction, then this is what I'll get. 2 I naught, negative 2 I naught because it's entering the node, plus Ix, okay? And then you have plus Is is equals to 0. We agree, right? This is equals to negative 2 times 2 plus, okay? In this case, what I'm going to do is, if this was negative, right? So minus 1, okay? So now what we'll do is, entering the node was negative, leaving the node is positive, right? Oh, I'm sorry. Minus of minus is plus 4. Okay. All right, so in this case, now that you are taking, if you assume this direction, because it's opposite, then you have to take the current as negative 1, okay? But if you assume the true direction, then your current is plus 1, right? Because now it's not in the opposite direction. So now if I write this as plus 1, I won't be writing it minus 1 because I'm assuming true direction. Okay, so now Is will be equal to, again, 3 amps. Okay, so you get this here. Okay, so let's go for the next source. I'll do the dependent source, and I'd like you to try the independent source. Okay, so over here, what I'm gonna do is, I'm gonna take a look at this network, right? This construction here with these two, and I'll show you why this is important, okay? You'll do exactly the same thing for these two. Okay, and I'll show you why we need to consider this branch when we are talking about the power for the source. Okay, so I'll rerun this here just for clarity so that we have ample space to analyze this, and then we'll calculate the power. Okay, so this was 10 volts, right? And we know the current, which is equals to 2 times I naught, which is equals to 4 amps, and that's flowing in this direction. Okay. All right. This is your node M, and this is your node A. Okay. We already decided that this was our current. Okay. This was our assumed direction here, Ix, which was equal to negative 1. Okay. And our voltage was here. We assumed this was plus. Okay, all right. Let's call this source as dependent source. It's a current dependent source, so we'll call this as ID. Okay, so we want to find the power of the independent current source. Okay, so that should be equal to the voltage plus or minus the voltage across it times the current, right? Okay, we know the current. Okay, we know the current is given to us. This current is nothing but 2 times I naught. Okay, the current is 2 times I naught because it's a current source. How about the voltage? What is the voltage across the source? What will be the voltage across the source? V10, exactly, V10 parallel, so they are V10, so this is V10. Okay, so V10 is the voltage across the source. So same concept here, when you're doing this source, the voltage across will be V30, okay? So because they are in parallel, you will exactly apply the same voltage across this. Okay, so all you have to do is just look for a parallel element whenever you're having a current source to take that voltage. Okay, so let's first calculate V10 over here so that we can use it in this case. So V10, as you know, is the resistance times the current flowing through it. So 10 times Ix. Okay, which is going to be 10 times minus 1, which is negative 10 volts. Okay, which once again means the polarity is reversed because the current is actually flowing the opposite direction. So plus should be here and minus should be here. Okay, and that's why we get a negative sign. Okay, with that understanding, let's go here. And what I'll do is, if we assume this is the same voltage, then the voltage across this current source should also be plus over here and minus over here. This will be, okay, so current is entering the positive. So I'll go here and I'll write this as PID is equals to plus voltage across it times the current, which we know from here, this, okay, V10 times ID. Okay, current entering the positive, so power is positive. So V10 is minus 10. Okay, this is V10 times ID, which is 4. So, I'd like you guys to try this one just for practice, and then you, once you try it out, you won't forget it. So that should be good for you to just test it. Okay, you already know the current. Okay, this is plus and this is minus. Okay, so current is entering the negative. So you write power of the 5 amp source will be equal to minus voltage across the 5 amp source times the current. Okay, of the 5 amp. Okay, voltage across the 5 amp is nothing but voltage across 30 ohms. Okay, and then you already know the current, you know this, so that will be 60 times 5. Okay, this will be 5. Yep. Why is the voltage? The voltage is not negative. The power is negative. We are writing it because we need to pick a sign, plus or minus. So if current enters the negative or leaves the positive, then power is negative. Okay? If current is entering the positive or leaves the negative, then power is positive. Okay? So depending upon which sign it enters, power will assume that sign. Okay, let's look at a slightly different problem, which is also interesting, so let's go here. find I1, I2, and I0.
Negative.
Okay, so here V0 is the voltage across V. This is V. Okay, so first, try to find V0. Tell me what you get for V0. Let me explain one thing. Everything that we need to find in this circuit is on the right-hand side, okay? So the only thing that drives the right-hand side of the circuit is this dependent source, which depends upon V0. So we cannot solve this side of the circuit until we know V0, because if we know V0, then we know this value. And then we can find everything here, okay? So our job first is to find what is V0. Any answer for V0? Okay, let me do it. I'll show you a simple method, and then I'll also show you, in case you're ever confused, you can simply try it like this. Okay. If you look at this circuit, right? Six, right, that's correct. Okay, these two elements are in series, right? You look at 12 and 6, they are in series. So you can combine them directly by adding. Okay, so in this branch, you can say R total, which is the total resistance here, will be equal to 12 plus 6, which is equal to 18 ohms. All right. Now, if I assume a current flowing through this like this, right? Let's say that current is equals to, we'll just call it as I. Excuse me. Okay, we'll just call it as I. So I will be equal to the source V over the total resistance. Okay, which is nothing but 18 volts divided by 18 ohms. That's going to be equal to 1. Okay, so 1 amp flows through 12, and the same 1 amp flows to 6. Okay, so V naught, right? V naught was nothing but the resistance times the current I. Resistance is 6 times I. So that will be equal to 6 times 1, which is equal to 6 volts. That is one way of doing it. Okay. But a very simple way of doing this is if you look at this circuit, right? And that's why in the previous class we went over a discussion of a voltage divider circuit, right? So here you have a plus minus 18 volts. Okay. You have two resistances. I'm just going to redraw this slightly differently. Okay. This being 12 and this being 6. Okay. What we need to find is what is the voltage across the 6 ohms. Okay. We don't care about the voltage across the 12 ohms. Okay. So if you look here, they are in the ratio of 1:2. Okay. So obviously this total voltage will be divided in that ratio. So if you remember the voltage divider rule, okay, we said V naught will be equal to the total voltage, Vs, times R1 divided by R1 plus R2. Right? You can write it as V1 if you want to calculate V1, V2. So in our case, we need V naught. V naught is nothing but the total voltage, 18, times the resistance 6, divided by 6 plus 12. So 6 plus 12 is 18, 18 will cancel, that will be 6 volts. Okay, so if you use voltage divider, it actually makes things a little easier. Okay, so we know if this is 6 volts, let's call this as dependent source ID. Okay. So ID will be equal to okay? ID is 3 amps. All right, so here's what we'll do. We need two equations to solve for I1 and I2, okay? So what we're going to do is, let's take, for example, let's consider this node N. Okay, ID is this current, right? So this current is flowing like this. Okay, because it's leaving. This current flows out and that flows out, right? So I'm going to go here and say KCL and N. Okay, so if this current is actually flowing downwards, it should come from this node like this. So since all the currents are leaving the node, then I can go here and I can write this as ID plus I1 plus I2 is equals to 0. Okay. We don't know I1, I2, but we know ID. ID is 3 amps. So I1 plus I2 should be equal to negative ID, which is equals to negative 3 amps. You can do a current division and you can do this simply. If you remember the current division rule, just as a voltage divider, you know the total current, you can substitute these values and you can get I1, I2 directly. But I'll do it the other way so that you guys have an idea of using KVL, KCL. Okay. All right. So this is a, let me put this here. This is a alternative to this, right? This is an alternative approach. Using voltage divider is an alternative to this, right? I'll show you the other one also using current division. Okay. All right, let's go here and we'll do one thing. We'll just take a loop here, okay? I'm going to assume this to be V10 because current is flowing downwards. I'll assume this to be V5. Okay, so if I do a simple KVL here like this, okay, there are only two voltages, okay, KVL in mesh 1. Okay, so plus 5 plus V5 minus V10 should be equal to 0. Okay, there's nothing else present there. Okay, V5 is nothing but 5 times I2, or write this as 5 times I2. Okay, minus 10 times I1, or write this as 10 times I1. Okay, so in other words, if you take 5 common, I2 is equal to 2 times I1. Okay, if you solve these two, you'll get I1 and I2. Right? should be -1, and I2 should be -2. Only then you get -3. Okay, all right. So we found out I1 and I2, okay, these two currents are done. Okay. Now, before we go to, this is to find I1 and I2, right? So in this case, I'll show you a different way in a moment. In 1 second I'll show you. But let's talk about I0 for a brief moment, okay? Looking at the diagram, what can you tell me about I0? What should be I0?
Is it -3?
-3? Okay. So if you look at, okay, let me tell you one thing. So you have, for example, -1 coming here. Okay, this is I1 is -1, right? So this is -1, and this is -2.
Should be 0 M. Yes, -2, -2.
Right.
And then the 3.
ID is 3, right? So ID is 3.
Oh.
Right? So it adds up to 0. Sum of all the currents at any node should be 0, right? So if I take over here, actually these 3 points are the same because nothing is connected between them. So the sigma I, wherever you might want to do that, is equals to 0. Okay? So what does it tell you about I0? What should be I0? Huh? 3. If you put, okay, so let's assume one answer is 3. Any other answer? I think somebody just whispered it, but
0?
0. Right? 0, because anything non-zero will make sigma non-zero, right? At this point, if I0 is equals to 0, sum of all the currents is 0, okay? And why is that? See, whenever you look, you don't even have to do any of it. Just look at any current, right? If the current enters from here, it leaves from here, right? If this current is entering from this end, it's leaving from the other end. If the current goes this way, how is it going to come back? Because there is no connection here. Okay? So, for a current to flow, there should always be a closed loop. So for example, if I0 is going this way, right? It has to go around and come back to the source. If I disconnect this, I0 immediately becomes 0 because there is no path for it to come back. If I0 flows here, it has to come back from the other side, right? If there is no connection, whenever you look at a bulb, right? You have, let's say you have a light bulb like this. You have 2 wires, right, for the current to flow like this and return back. If you disconnect this, there's nothing. Okay? So always, the only reason that this has been disconnected, you don't have to do anything. You can just look at this and you can tell that there is no return path for I0. Okay? Mathematically, you can also show it here. Let's try to do KCL at this node K. Let's call this node as K. Okay? If I do KCL at K, right? ID is coming in, right? Let's take I0 first. So plus I0 because it's leaving the node. ID coming in minus, okay? These 2 currents are also coming in, -1, -2. Okay? So I0 minus 3 minus of -1 minus of -2 is equals to 0. So I0 is equals to minus. Okay? All right? So even if you try to do it like that, you'll get your, okay? So just remember, current always needs a closed loop, okay? Even though you can have a very large voltage here. If there is not you don't have a closed path for the current to flow, it's not going to work. That's why we have switches, because they disconnect the path, okay? All right, so let me quickly show you a simpler way of doing this, using just as we did the voltage divider, can we use current division for this, okay? And I'll do that as an alternative to this approach, okay? So an alternative to this approach, okay, is to use the current divider rule. Okay, just as an alternative to this, we use the voltage divider. In this side, we use voltage division. Here you can use current division. Okay, so here you can use voltage division. On this side, you can use current division. Okay, so I'm just going to draw this part of the circuit here, and we'll fill in the rest. Okay. So we'll get the magnitude, but let me explain. The only problem is understanding direction. Okay. All right. So because the current is flowing like this, right? We'll assume here.
So rule to go on the big part like that is go on the loop and divide it. And instead of I1 going and I2 going down, we go up because we go around. Then I will meet on top.
No,
The 3 amps.
3 amps. What about the 3 amps?
No, I'm saying I1 and I2, they find the opposite
Yeah.
direction, so they will meet on the node on top, so we give the 3 amps and the ID.
Correct. Okay. So what we're trying to do here is current division, right? So let's say that this 3 amps is flowing like this, okay? It gets to this node M, or we call it any node. We'll call it as M, okay? So at this point, it's supposed to divide, right? So let's call this as I1X, okay? And over here, it divides as I2X. All right, I1X and I2X. So in a branch, you cannot have two currents, okay? You simply cannot have two currents flowing in opposite directions. Essentially, they are the same, but since they are opposite in direction, we'll write it as I1 will be equal to minus I1X, and I2 will be equal to negative I2X, because the direction is opposite. Okay, that's it. Okay, because this current comes here, and it splits, okay? But the book has given us directions like this, but in fact, the current is flowing, so we'll write it in opposite direction, okay? So by current division, what is the current IX? Okay, so if you remember current division rule, I'll just draw a small circuit here. If you have, for example, IS like this, okay, and you have two branches, this is R1, R2, okay, this current being I1, this current being I2, okay. So we say that I1 will be equal to total current times the opposite resistance divided by the total resistance. Okay, same thing with I2. Okay, this will be equal to the total current, opposite resistance divided by the total resistance. Okay, I1 and I2. So we'll do the same thing here. Okay, so I1, which will be equal to negative IX, right? IX means the total current ID times, let me write it as 3. Okay, times the opposite resistance. If I'm finding I1, I'll take this resistance 5. Okay, so this will be 15, so that will be equal to negative 1. Okay, let's go here. 2 will be equal to minus 3 times okay, so you get the same thing as previously. But this is using current divider. So if you don't want to do KVL, KCL, you can simply do voltage divider and current divider. If you use these two, you can also solve it like that. Okay, but you need to understand how to set up the voltage and current division. Okay, let's take one final problem on this topic and then we'll exit to a different subject. Okay, this should be easy. All of you should be able to solve this pretty straightforward. Here you have a source, which is 20 volts. Once again, exactly like the last case, you have 450 and 150 here. Okay, and this is V0. Okay, here you have, so just a two-step process. You should be able to find this very easily. This is V0 divided by something. I'll tell you what that value is. It is V0 divided by 100. This is 300 ohms. You need to find this voltage Vx. That's it. Okay. Very straightforward, find Vx. If you're able to do this, that should be good. First find V0. Once you find V0, you know this current, okay, because this is a dependent current source, and you can find this voltage. That's it. What's V0? So if you do voltage division, V0 will be equal to total voltage times 150 divided by, right? So this will be 20 times 150 divided by 600. Okay, so that will be equal to 5 volts. 1 over 4. Okay. All right. Let's call this current as ID. Okay. So if ID is equals to naught is 5. Okay, or you can leave it like this for now. Okay. So ID that leaves this terminal will go down like this through the 300 ohms. Right? It'll go around and it'll come back from here, right? It'll go like this and it'll go. Okay. So if you want to find Vx, Vx is nothing but the voltage across the 300 ohms. Okay. So by Ohm's law, that's nothing but the resistance times the current. Okay. The resistance, as you know, is 300 times the current is ID. So this is okay. V is equals to IR or I. So here, what you'll do is just say 300 times ID. Yes, sir.
Why did you use 150 instead of 450 for the 200?
Why did I, in the numerator, you mean? Yeah. Why did I use 150? Okay. So, with current division, right, voltage division, whenever you have plus, like let's say you have two resistors, R1 and R2. Okay. Let's say the voltage across each one of them is V1 and V2. Let's say this is V1 and let's say this is V2. Okay. This voltage V1 will be equal to the total voltage Vs times R1 divided by the total resistance. Okay? If I want this, V2 will be equal to Vs R2 divided by the total resistance. Okay. So, depending upon the voltage across which resistor you want to calculate across, you'll take that. Since V0 happens to be the voltage across 150, I write it as 150. If I wanted it around 450, I would have written it as 450. This is your voltage division. Okay, with that, so that was pretty much all our discussion and our work with KCL and KVL. Okay. All right. So we'll move to a different circuit analysis technique. Okay. The idea with circuit analysis as we move forward is you can solve a circuit using any one of these rules. Okay, we'll explore a couple more. Any one of these methods should be fine, or they should be adequate to solve circuits. But as we keep on investigating other approaches, the goal here is to use minimum number of equations to describe the circuit, right? So for example, I had to write a voltage division here and then do one more rule here. Or you have seen in the previous case, we used KCL and KVL. How about writing just one equation or two equations and so on? So the idea is, we'll come up with methods or techniques that help us describe the behavior of the circuit with minimal number of equations, okay? That doesn't mean that you cannot use any one of these that we have previously worked on. All of them are perfectly fine. And as you go forward with circuit theory, you can pick a method that you're most comfortable with and you can use that. But since we are studying these methods, it's good to know all of them, because if you're referring to somebody else's work and if they have used one of the other methods, you should know how they got to a particular answer, or in some cases, one method is more applicable or more easier to reach a conclusion than the other, so we'll try to look at it. Okay? All right. So, and this is the method that we'll be talking about now, is a very simple method. If you just get an idea of how to work with it, it's straightforward, and probably this is the easiest of all of them, okay? We call this as node voltage. Okay, we call this as node voltage method. Okay, or it's also referred to as nodal analysis, okay, or doing the nodal analysis of the circuit. Okay. Node voltage or nodal analysis. What is node voltage? Okay, so let's assume we already know KCL, KVL, right? So if you take the KCL and you write it in a different way, it becomes nodal analysis. Okay, so let me explain. Let's take a node N. Okay, let's say that I have, let's say I have R1, R2, R3, R4. Okay, right. I'm just, for now, I'm only going to assume leading currents. Okay, I'm only going to assume this is I2, I1, I4, and I3. Okay. So if I do KCL at node N, okay, since all of them are leaving currents, I can say sigma I at node N is equal to 0, which is I1 plus I2 plus I3 plus I4 is equal to 0. Okay, all right. So this is our typical KCL, or Kirchhoff's current law. Okay, but I can, if I know the voltage at the other end, I can actually describe the circuit in greater detail, which is, if I can write each of one of these curves, for instance, since this is N, we'll call this node voltage here as Vn. Okay, we'll call this as Vn, right? And let's say this end was V1. Okay, so the current is flowing from Vn to V1. So I1 will be equal to Vn minus V1 divided by R1. Okay, how did I get that? If you have a wire like this, right, just as we did in the lab experiment, right, you have A and this is B. We measure the voltage across these two by connecting the terminals here. That means we are measuring the difference between two, right? If the current is flowing like this from A to B, we say I is equals to VA minus VB divided by R, which is voltage divided by the resistance. If this voltage becomes 0, which means VA equal to VB, there is no current. Okay? If it happens to be flowing like this, then I'll write it as VB minus VA. Okay? Whatever is the larger voltage, we write first. Okay? So if it flows from A to B, we'll write it as VA minus VB. If it flows from B to A, we'll write it as VB minus VA. Okay? Since it's flowing from N to 1, we write it as Vn minus V1 divided by R1. Okay? Same thing, let's assume the voltage here was V2. So this current would be Vn minus V2 divided by R2. Okay? If this was V3. Okay? And so on, right? So this entire expression, okay, I can write this as Vn minus V1 divided by R1 plus Vn minus V2 divided by R2 plus Vn minus V3 okay, provided this is V4. Okay. All right. So if you just rewrite this in a voltage divided by resistance form, which is nothing but Ohm's law, V over R is current. This is your node voltage expression. Okay. This is nothing but your KCL. Only thing is, instead of writing the currents, we write it as difference of voltage divided by the resistance. Okay, that's it. Okay, this is your node and or we call this as node voltage equation. Okay, that's it. Okay, there is nothing else to it. Only thing that we want to write here is our currents. Okay, each one of them is a current. Okay, this is nothing but I1, this is I2, this is I3, and this is I4. Okay. All right. Now, all it helps us do is bring in more variables so we can easily solve for it. That way we don't need more equations or extra equations to involve these nodes. Okay. Otherwise, if I just write a current equation, then these nodes are not involved directly, so now we can involve them directly within the equation. Okay? So what I'll do is I'll just set up a couple of sample circuits where we'll simply write a expression, and once we know how to write the expressions, we'll take up a simple problem to solve. Okay? All right. So let's take this circuit for instance. Whenever we do node voltage, the very first step is to identify essential nodes. Okay, what is an essential node? Okay, step one, I'll write it as okay, identify okay, what is an essential node? Okay. Let's go back to the definition of a node. Okay. A node is where at least two or more elements meet, right? The minimum is two. For two elements to connect, that qualifies as a node. An essential node is nothing but where three or more elements meet. Okay. Okay. So node is two. Essential node will be three. Okay. So where are the essential nodes? This is a simple node because you have two elements meeting. Here you have three. So let's call this as an essential. Okay. You have one more essential node here. And this is an essential node because you have actually all of them are the same because there is nothing connected in between, so these two are the same node. Because there is nothing connected in between. Okay. If there was an element connected in between them, then it would be two different nodes, but since there is nothing connected in between them, it behaves as a short, so it will be the same node, or it will have the same voltage. Okay. So let's label these nodes. We'll call this as node A, node B, okay, and we'll call this as C. All right, node A, B, and C. Okay. Now, what we do is, whenever we write node voltage equations, we need a reference. So generally, since this node is connected right across everything, we'll assume this to be our ground node. Okay. So step two, assume one node as your reference. Okay, so we'll say for that node we'll assume that as a reference 0. Okay, just as our ground is a reference for all voltages, with it being 0, in this case we'll assume one of them as ground, so we'll assume this to be ground. Okay, every node voltage circuit you'll see one node being marked as ground as your reference. Okay, now what we'll do is the last step is write the node voltage equations with respect to the other nodes. Okay, with respect to the other nodes. Okay, the other nodes here being A and B. Okay, all right. It's very simple. First, identify essential nodes. Mark one node as being a ground. Okay, typically we take it as the bottom node like that, which runs across the circuit. And finally, we'll write the expressions. Okay, so let me write for B, and then what you'll do is we'll work on A. Okay, or let me try A first. Okay, let's do A first. Okay. So I'll go here and I'll say node voltage and A. All right. Keep in mind that this is just like KCL. Because there are 3 branches connected here, it'll have 3 terms that will sum up. Okay. So let's start from the easiest is here. Okay. So here we'll say VA minus VB, okay, which is on this side, okay, divided by the resistance, R5. Okay. We always take the node that you're writing the node voltage equation about as the first voltage, and then we'll take the other one as the negative voltage. Okay. So when we go here, right, we finished this part, right? Now we'll go here. So this will be VA minus VC divided by R2. Okay, plus we go here. Okay, VA at this node the voltage is 100, right? Because this is the 100 volts, right? We always want to take the difference of the 2 voltages. Okay, so VA minus 100 divided by R1. That's it. Okay, always take the difference of the 2 and just write the voltage. Okay, I want you to try writing for VB, okay, node voltage at B. Okay, when you write the node voltage expression for B, B comes first, okay, we'll do VB minus everything. Okay, so here, let me go here and say node voltage at B. Okay. So we'll start once again from here, let's say VB minus VA divided by R5. Okay, then let's go here, VB minus VC divided by R3. Okay, and then let's go here, VB, and the other end is again VC divided by R4. Okay, that's it. Okay, simple, nothing too complicated. Just make a count of how many branches are connected at one particular node. That many terms you should have in your final expression. Okay, always take the difference of the voltages divided by the resistance. Okay. There is only one special case. Okay, one special case where sometimes the circuit will be like this. Okay, let me show you here. Like this for- Just want to demonstrate one particular point with you so that we are on the same page when it comes to writing equations. Okay. All right, so these two are our essential nodes, A, B. Okay, as always, let's assume this to be C. This will also be C. Okay, now what I'll do is, let's write this voltage at A. So that'll be VA minus the voltage at this point is V1, right? Just as it was 100 here, we wrote it as minus 100. Okay, so here at this node, if it's V1, that'll be VA minus V1, right? So I'm going to go here. Okay, so let's say this is our branch 1, 2, 3. Okay, 1, 2, and 3. All right. For 1, it's nothing but VA minus V1 divided by R. Okay. I'll do 3 first and then I'll come back to 2 because it's a little different. Okay. Here, this will be VA minus VB divided by R2. Okay. All right. Now, here, if I want to subtract the voltage, we don't know the voltage across the source I2. Okay. So it creates a problem for us to write it as a difference of the voltages. Okay. But what does this whole thing represent? What does it actually represent? What does this mean? What is this? It's the current in this branch, that's it. Voltage divided by the resistance is the current. This is nothing but the current in this branch, okay? So, if I need to write anything here, which is the current, then I already have the current flowing through like this. So if you see a current source in the branch, you don't have to do this. You can simply write a current, okay? But just keep in mind, incoming currents are always negative, leaving currents are positive. So here, I'll simply write this as minus, because each one of them represents a current. Let me reverse the direction so we can have a plus term. Okay, okay, all we are trying to do is represent current. So if a current is directly available to us, we'll write it as current. We don't have to write it as voltage divided by something, okay? So incoming currents, keep in mind, once again, I'll write it here, okay? Current entering the node. Is negative. Current leaving the node is always positive. Okay. All right. So with that in mind, let's write the expression for B. Okay. So if I do node voltage and B. All right. We'll start from here. VB minus VA divided by R2. So this branch will be VB minus VA divided by R2. Okay. Then we'll have this branch, which will give us VB minus VC divided by R5. Okay, and finally, this branch where you already have a leaving current, okay, so you don't need to do anything, so this branch will give us simply plus I1 because it's leaving the loop. Okay, since it's leaving B, you write it as plus. If it was entering B, you write it as negative. Okay. All right, so let's stop here. What we'll do is we'll once again shortly review that and start with some